Cerno Bioscience. In order to understand the Cerno calibration approach, let's first examine the current classical approach to mass spec calibration. First, it is very important to understand that mass spec data is not acquired as centroid data, the stick-like representations of a mass spectrum. Mass spec data is acquired as a continuum and then processed by the mass spec data station or firmware to locate the peaks and present the results in centroid form. The instrument must be calibrated using one or more known standard ions before accurate mass results can be obtained. The standard ions are measured and then their peak location is determined. Accurate location of the peaks ultimately determines how well the calibration performs. Current approaches typically use only the topmost points of the monoisotope peaks to identify the peak's mass position. In addition, the peak picking algorithms are empirically based and can be in substantial error in the presence of noise. Another complication arises from the fact that mass spec data peaks are usually quite asymmetric and dependent upon the instrument tune. Note here, in this example, the substantial lack of peak symmetry. This makes consistent determination of the true peak position difficult when using the traditional approaches, particularly if only a few data points over the top of the peak are used for peak location. Once the peak location is determined, the data is then shifted along the x-axis to its theoretical calibration location. In most instances, the profile data is then discarded along with any information they may contain, and the peak position is marked with the classic MS stick or centroid data. Cerno's patented approach to mass spec calibration takes full advantage of the theoretical basis of mass spectrometry to create a proper calibration function. Not only does this approach accurately locate the peak positions, but it also suppresses the noise and, most importantly, corrects the peak shapes to a mathematically defined function. This is made possible due to the fact that mass spectrometry is one of the few analytical measurement techniques where we can accurately calculate a theoretical spectrum. This is possible because we know both the mass of a given ion and the isotope distribution to a very high degree of accuracy. Let's see how it works. First, the calibration standard ion is measured with the data acquired in profile mode. Cerno's calibration can only function with the profile mode data. Once the data is centroided, all the necessary information to do a proper calibration or recalibration is lost. This profile spectrum is the standard from which we will derive our calibration. MassWorks first examines the standard ion and calculates a mathematically defined line shape that closely approximates the measured line shape. For example, it may be determined that the measured line shape is closely approximated to a Gaussian line shape whose half-width is 0.32 Daltons. This mathematically defined line shape will now be used as the new target line shape for instrument calibration. Next, knowing the formula for the standard ion, we calculate the theoretical mass spectrum. As mentioned previously, this can be done to a very high degree of accuracy because the masses of the elements are known very accurately, as well as the natural abundance of the isotopes. Note that this theoretical spectrum has infinite resolution and the contributions of the different isotopes in the n+1, n+2, and remaining isotope peaks are quite apparent. However, our real measurement does not have infinite resolution, but we know the approximate resolution from our peak shape estimation. Now, if we simply convolve that defined peak shape function with our theoretical spectrum, we have determined the ideal mathematically defined theoretical spectrum. This is our target calibration function. Then, we simply compare this ideal theoretical spectrum against the measured spectrum. From these two functions, we can now derive a calibration equation, which when applied to the measured spectrum gives us back a spectrum that is identical to the theoretical spectrum within the limitations of the noise in the measured data. Once we have the calibration equation, We can then apply it to any measured data to obtain a spectrum which is not only calibrated in mass, but line shape as well. It is important to understand that this calibration equation is independent of the calibration ion and truly reflects a correction of the instrument's inherent measurement errors. Once the calibration equation is calculated, it is a simple matter to apply it to the measured data. The calibration is applied to the measured data and a fully calibrated spectrum is obtained. The calibration corrects both the mass position and the line shape of the spectrum to a mathematically defined function. Comparing the calibrated and uncalibrated data, it is clear that the mass